Today is the last day of our FDP. So we are going to start with a valedictory session. For that, we have three guests in our event. Today, present three guests in our event. I will call them one by one to just give a brief idea about the event, how it is going on, why is it important, and all those things. So first, I am going to call or introduce uh, Chief Managing Director of Research Foundation of India, who is Dr. Ashok Kumar Gupta. Dr. Ashok Kumar Gupta is having BE from MA NIT Bhopal, PGDM from AIMA New Delhi, LLB from KP College, MTech from MA NIT Bhopal, DMS from NIM New Delhi, PhD from AISCT University Bhopal. He has published more than 50 research papers in national and international journals. He is having a rich 40 years experience, around 30 years in the industrial field and around 10 years in the educational field. Recently, Dr. Ashok has also visited USA and various renowned universities like Northeastern University, Boston, USA, Harvard University, MIT Boston University, etc. As far as association with RFI is concerned, he is considered as one of the founder member of RFI. Looking to his dedication and hard work, he now got promoted as CMD, which is Chief Managing Director. So I welcome you, sir, to just give your opinion regarding this FDP. Over to you, sir.
Thank you, ma'am.
Yes.
Hello, everyone. This is Professor Dr. Ashok Kumar Gupta, CMD RFI from Delhi NCR. I feel honored to be invited to this valedictory function of workshop on essentials for machine learning. The aim of this workshop was to provide the most complete and reliable source of information on the recent advancements in the field. The workshop covered a broad range of topics in this field. Machine learning is based on the idea that machines should be able to learn and adopt through experience. Artificial intelligence refers to a broader idea where machines can execute tasks smartly. AI applies machine learning, deep learning, and other techniques to solve actual problems. Machine learning is the concept that a computer program can learn and adapt to new data without human intervention. Machine learning is a field of artificial intelligence that keeps a computer's built-in algorithms current regardless of changes in the worldwide economy. Now it's my privilege and honor to welcome all the dignitaries, resource persons, and experts available for this workshop, especially Dr. Sister Alice Thomas, Dr. Vaishali Dhingra, Dr. Vivek Kaushik, Dr. Shalu Kotwani, Professor Tanisha Dalal, Dr. Ravi Vyas, Dr. Ajay Patil, Dr. Saurabh Jain, and Dr. Ajay Jain sir. I am thankful to the entire team RFI and organizing institutes. I am thankful to all who have given their input in this workshop and all participants who made this workshop a success. Thanks for your passion. Thank you again. Over to you, ma'am. Thank you.
Thank you very much, sir. So our next guest is Dr. Swati Agarwal from Christ University, Delhi NCR. So over to okay. So Dr. Swati Agarwal has obtained her PhD from Devi Ahilya University, Indore. She has cleared CSIR UGC NET in the year 2004. She has 17 years of teaching experience. Presently, she is working as an associate professor in Christ University, Delhi NCR. Her area of research is inventory management of deteriorating items and supply chain management. She also has many publications in various national and international journals of repute. She has been resource person in few SPSS workshops as well. She is handling few many positions in this department as well. So I welcome you, ma'am. Over to you, ma'am. Yes, ma'am, you are audible. Voice is little bit low. That's it.
Just 1 second. I hope it is okay now.
Yes, ma'am, it is fine.
Okay, so thank you, Amita ma'am, for inviting me. So I think this is the right time to have such a workshop, because we all know that digitization has entered into all aspects of our life, right? From using mobiles to doing online transactions to health facilities, and everywhere the data is there, right? So these days we need there is a need to capture on this data, and you need to develop the models that can quickly learn and analyze such complex data. So that is why we plan to have such a machine learning or this workshop on machine learning techniques. And this workshop started with the basics of the mathematics and statistical techniques which are used in machine learning. And in this workshop, we have ended with the advanced techniques such as neural network and deep learning. And in today's session, we will be covering CNN and autoencoder. I believe that all the participants were greatly benefited by this FDP, and we will look forward to have many more such FDPs in futures, where we can go in a little more in depth of all these techniques. I would like to thank all the eminent speakers who have taken time out of their busy schedule for this FDP. And I would also like to thank all the participants who have actively participated.
Yes, ma'am. Okay, thank you, ma'am. Thank you, ma'am. So our next guest is from Sentence College for Women, Hyderabad. Professor Kavita, working as an assistant professor in Department of MCA, Sentence College for Women, Hyderabad. She has completed her MSc in Computer Science and MTech in Computer Science Engineering, and currently she is pursuing PhD also. She is an innovative and knowledgeable professional, having 19 years experience as a lecturer. She has attended many seminars and delivered various speeches as a guest faculty, and successfully organized a few workshops for the students. She has also many publications in national and international journals, and also filed a patent successfully. Professor Kavita has received 3 awards in her career. First is Global Eminent Teacher Award. Second is Outstanding Performer. Third is Best Placement Hit. And she has also received 100% attendance award for 2 academic years. So over to you, ma'am, and we welcome you. So over to you, ma'am.
Thank you, Amita.
Yes, ma'am.
Good afternoon, everyone. I'm Kavita, Placement Officer, Faculty, Department of Computer Science, St. Anne's College for Women, Mehdipatanam, Hyderabad. I would like to thank the organizers, Dr. Saurabh Jain, Chairman and Chief Executive Officer, Dr. Reshu Jain, President, Dr. Ashok Kumar Gupta, Chief Managing Director, Professor Ajay Jain, National Coordinator, Dr. Amita Soni, Assistant Professor, School of Sciences, Christ University, Delhi, for organizing such a fantastic 5-day FDP and also giving us the opportunity to be a part of this FDP as sponsors. I appreciate my colleagues Ms. Aparna and Ms. Renuka for utilizing this opportunity by delivering a few lectures on various topics. I congratulate all the resource persons from other different institutes as well. Nowadays, we are giving a lot of importance to machine learning as it is used in many applications which are essential in our daily life. Everywhere, like healthcare, automation, banking, image recognition, speech recognition, virtual personal assistant. For example, we all have seen recently, like, advertising like Alexa, play the music. This is also done with the help of machine learning techniques only, and language transition, etc. So I would like to suggest a few points to all the participants who all attended this FDP for 4 days or 3 days, that try to work on some statistical concepts. Be thorough with some programming language, like mainly I can prefer either Python language or R language, which are very essential for statistical concepts implementations. Set your goals. So this is very important for everybody, either it is a participant or a resource person. Because of that, will help you to avoid wasting your time and keep you moving forward. And also perform investigation on data analysis. Learn how to handle big data systems. and also look into deep learning methods like neural networks, autoencoders, which is the topic we're giving today. Do some data projects as well. Not only the projects which are related to data or not related to data. Some projects especially deals with only a particular data which is very essential for live projects especially. So like fake news detection, breast cancer classification. Actually, recently I have done one project using this breast cancer classification by collecting different types of data for different types of symptoms for breast cancer and all. So I can prefer this breast cancer classification predication actually using any one of the languages. And also predication of age and gender. So these are the main data projects I can suggest you all, participants who all attended for this FDP. I congratulate all the organizers and sponsors for making this 5-day FDP a successful event. I further appreciate all the participants for your involvement and sparing your valuable time for this event. We want to continue such associations with Christ University in the future. All the best. Thank you.
Thank you, ma'am. Is it over, ma'am?
Yes. Over. Okay. Thank you.
Yeah. Okay. Thank you so much, ma'am. So today again our session guest is Aparna, ma'am. So I welcome you, ma'am, again for the session. You have taken yesterday's session so nicely. So I want you to continue that as well today. So yesterday, Chandra Blasi ma'am has concluded this session with types of deep learning, which was one of CNN and autoencoder. So today Aparna ma'am is going to discuss more about that. What are those two components of deep learning? So over to you, ma'am. So ma'am will continue both the sessions for today.
Good afternoon, everybody. Am I clearly audible, Amita? Dr.
Yes,
Amita?
ma'am. Yes, ma'am. Yeah.
Okay. Let me share my screen. So, are the slides visible?
Yes, ma'am. It is visible.
Okay. So, very good afternoon, everyone, once again, and welcome to this session on convolutional neural networks. Like Dr. Amita was saying, towards the end of yesterday's sessions, we learned about the basics of deep learning. And today's session is going to be one specific kind of a neural network, which is the convolutional neural network. So before I even begin the session, I would like to quote Isaac Newton. Whatever we are doing, it is because of the advances and because of all the effort that has been already put out by a lot of accomplished people. These subjects, especially, like machine learning, deep learning, which are like in very recent subjects and newly evolving subjects. None of us obviously have studied them in the form of textbooks at our school or college level. So most of our learning is actually happening through maybe blog posts or through YouTube channels or through some really good MOOC websites like Coursera, especially the courses by Andrew Nog on Coursera. So, I would actually like to say that I'm very thankful and grateful for having the opportunity to learn and once again share it with all of you. So let's begin off with the CNNs. I would first like to go into a little detail about how a normal neural network works, because unless we understand what a regular neural network does, we won't really be able to appreciate the strength that a convolutional neural network brings in, and also why it is even necessary in the first place. We will move on to understanding some specific challenges that we face when we work with image data. As most of you might be aware, CNNs are especially suitable for image recognition tasks. So what is the speciality or what are the differences when it comes to data that is either in the form of images or videos, sometimes even speech? How does this differ from your regular structured data that is in the form of a table? So we'll understand a little bit about that. And then finally delve into what the actual convolution operation is all about and how it helps us in picking features from image data. We'll look at one or two really common and well-known CNN architectures and finally move on to a hands-on demo. So again, this part of the content was covered in the last session yesterday, which was the basics of deep learning. So what I have here is a very simple feed forward network. I would try to relate this to maybe, the session we had from supervised ML techniques yesterday. So those of you who can recollect from yesterday, we had a simple data set called as play tennis. There were 4 features. There was one final target variable. In a similar sense, even with deep learning also, you have your data. So all the values in your data set become these input nodes, x1, x2, x3, so on. So if it was that same play tennis data set, I would have 4 input values, x1, x2, x3, x4. Plus, usually there is one bias term also that is added in a simple plain vanilla deep learning neural network. So you would have 5 input terms, and each of these input terms would have some kind of a weight associated with it. Let's try to understand in more simple terms, what this whole concept of weights mean. For example, let us say I'm trying to decide if a student will do well in a given exam or not. There could be certain factors that will impact their performance in the exam. One is obviously how much of time they spend studying. One factor could be how much of time, maybe that they spend on social media that will actually negatively impact their score. Another factor could be the IQ of the student. Another factor could be the difficulty level of the exam. And when supposing, we are trying to create a model that will make use of all these factors and help us in predicting how a student might perform, we might give different kinds of weightages to each of these input attributes or features. We might give some kind of a positive weight to the amount of hours spent studying. At the same time, we might be able to assign some kind of a negative weight to the amount of time that a student spends on social media, because that is going to negatively impact. So these set of weights typically within a deep learning neural network are randomly initialized. And this is the basic working of a single neuron. The input feature or the attribute value into its multiplied with its corresponding weight value and a summation of all of this. So x1 into w1 plus x2 into w2, so on, along with the bias term that is introduced. So this is the basic summation that happens within a single neuron or a single neural cell within your network. This output is then passed through some kind of an activation function. There are many choices of activation functions. We could use a sigmoid function. CNNs especially make use of the rectified linear units. So we will talk about that in detail a little later on. So you have your summation, which is passed through an activation function that finally leads to some output. Let's try to understand this more in terms of, how our own internal neural structures work. The whole deep learning neural networks, they have been designed to kind of mimic the kind of neural structures that we have within our brains and the kind of processing that we do. Now, for example, if we are exposed to some kind of a stimulus, let us say, I look at a flower, or I look at a picture of a person that I'm fond of, I might have many billions of neurons within my brain, but only a certain section of those neurons will actually light up, or some kind of stimuli is passed through those neurons. Okay. A similar thing happens even within neural networks as well. Although you might have a lot of neurons at each layer, not every neuron contributes, or not every neuron is actually involved in trying to learn some kind of new information. So only a subset of those neurons are activated, and that is what this activation function actually does. So our reason behind using this activation function is to make sure that only certain subset of neurons from each layer are involved in learning any kind of knowledge or information from whatever processing is happening. A simple neural network actually, maybe you would be able to feed in, let us say, images of maybe, a lot of animals or human beings or cars or objects put together, and then you train your neural network. Finally, it should be able to classify that this picture 1 has an image of a cat, maybe this picture 2 has an image of a dog. So what we are expecting our neural network to actually learn is to look at the image and by itself learn what is that image about, or what are all the various objects present within that neural network. So typical neural networks for image classification, what they do is we input maybe, hundreds or sometimes even thousands of images into the neural network. It goes through this whole training process where it tries to learn what each image is about. Finally, either, you can give a new image, it will be able to tell you exactly what that image is about. So still we are following pretty much the structured, supervised way of doing things. Now, this is a small animation I have of how, what we have seen on the previous screen of how artificial neuron works like. So these are my input attributes, x0, x1, x2. These are the set of weights, w0, w1, w2. All of them are being fed into my neuron. Like we said, we are going to do w0 into 1 plus. So we have the whole summation. This entire summation is being passed through this activation function, which will finally lead to some kind of an output. So this is the working of a single neuron. Now, a typical neural network consists of, maybe thousands or sometimes even millions of neurons. So you might have many thousands of neurons at each single layer. So a simple feed-forward neural network takes its input. Okay, so we already have the input which comes from our input data. We start off with some kind of random weights. And this is a fully connected network. If you notice, every node at the input layer is connected to all the nodes at the first hidden layer. You might have many hidden layers also. This is a really small network as such. And each of these nodes, N1, N2, N3, will have some final output based on what activation occurs over here. That finally is being fed once again into the output layer. And this output layer is what helps us in doing our classification task. The power of neural networks actually comes in once we start applying the principle of back propagation. So what this means is, again, I'm trying to maybe use some really simplistic examples so that the concept becomes clear. Supposing I'm, let us say, taking a class and then explain a concept, and I ask the students some kind of review questions. That will help me identify whether or not they understood the concept. Now, if I realize that, there are some gaps in the knowledge, I can probably use some more examples or maybe go in depth to see that those concepts are once again clearly explained and the students actually get those concepts. A neural network also uses some similar kind of a logic. So once you train your neural network with your input data and you come out with some kind of a final output, you check this output with existing output. Like we said, this is a supervised situation. So we already know the final answers as such. The final target labels are already available to us. So maybe, your neural network says this image is an image of a cat. Maybe in reality, that could have been an image of a dog. So there is some kind of error that is actually creeping into the network. So then we take derivatives, with respect to this error and back propagate the error through the network. What this process does is it helps us in modifying the weights. Okay. So for example, again, if we go back to our student example, maybe 1 hour of studying plus half an hour of social media is giving me, let us say, 70% of marks. Now, maybe if I say 2 hours of studying plus 10 minutes of social media might actually give me 90% result. So the amount of times that we are associating with each of those features, I'm changing. In the same way, whatever initial set of weights that we started with, we are going to back propagate the error and modify the weights. So what the neural network is actually doing is it is training itself, or it is trying to learn how to get to the correct output in a repeated fashion. So data goes in a forward pass, gives you some output, you calculate the amount of error that has happened, you use that error, go back through the network in order to modify your weights. Now you do a forward pass once again with your original input data and these modified weights. So once you have done this process repeatedly over a period of time, all the weights you will have achieved, the correct or optimum set of weights that will give you really good accuracy at your output layer. So this is actually the background with respect to a regular, normal, deep neural network. We also refer to them as feed-forward neural networks. One specific kind of a feed-forward network happens to be the multi-layer perceptron, which was covered in yesterday's session. A multi-layer perceptron, in fact, has fully connected hidden layers. Like we just discussed, they make use of the backpropagation algorithm in order to adjust the weights. The number of neurons at the output layer are equivalent to the number of target classes. So, for example, if I am trying to create a program that is going to classify, or actually this is actually a very common problem or a very common data set that is used within deep learning scenario, digit recognition, number recognition. So we are all aware, we have like these 10 digits, 0, 1, 2, 3, 4 till 9. So the number of target classes that I'm interested in is 10. So I might have a lot of neurons right from the input layer to all the hidden layers, but at my last layer, which is my output layer, the number of neurons are going to be 10, each one to predict whether it's a 0 or a 1 until 9. Okay. Now, the biggest problem that comes with these deep learning neural networks is the number of weights that we are supposed to initialize. Again, the network will randomly initialize all these weights. And as we said, in the backprop process, it is going to modify those weights accordingly. Now, imagine if your input is a small image that is of size 64 pixels by 64 pixels. So it is going to be like this graph kind of a structure, 64 by 64. And we are saying grayscale. I'll show you the grayscale versus RGB in a little while. So each of these pixels, you can just imagine like a graph paper with 64 rows and 64 columns. Each cell has some kind of a number between 0 to 255. So this is how the data will be represented internally for the neural network. When I look at it, it is a picture. But that picture ultimately, when it becomes input to my neural network, it is going to be this 64 by 64 vector. Now, if you have 64 by 64 into 1 nodes at the input layer, that is, you have 4096 values. I'm going to go back to the slide. Here I'm showing you just 2 neurons at the input layer. Right now, the example we are considering like this, x1, x2, x3, you're going to have till x 4096. That's what we are saying. And then let us assume the next layer has 500 nodes. Again, if you notice, here I have 2 input nodes and I have 3 nodes in my first hidden layer. If we count these number of lines or connections, 1, 2, 3, 4, 5, and 6. Okay, so there are 6 connections. This is a 2 into 3. Okay, a simple formula, m into n. Now, the example that we are considering, we are saying we have 64 by 64, 4096 nodes here, and I have 500 neurons here in my first hidden layer. So the number of these connections or weights that we will have to initialize becomes 4096 into 500. And again, this is actually a really simple network as such, So with a simple, fully connected neural network, right at the first stage, these many number of random weights you will have to initialize before you even begin training your neural network. And as the size of your input images increases, and as the number of nodes in your layers increases, you can only imagine these number of weights that you have to initialize will go up drastically. Let's see, what happens. Now, like I said, since CNNs are typically used for image recognition or image classification processes, your images can either be in grayscale or they can be in the form of color images. When we say grayscale, this is a typical grayscale image. The entire coloring is ranging anywhere in between 0 and 255 or in between black and white. Now, for example, if you see the small animation towards the right-hand side, what we have is an image of the number 8. And there are certain places where it is really dark. Those pixel values, if you notice, it is 250, 253. If you see the corner of this image, it is white. Okay, so this pixel value is 0. So this image of 8, once it is actually fed into the neural network, it becomes this 2 by 2 matrix of this set of numbers. Most of the time, we might be dealing with colored images as well. So if it is a RGB image, your original image is actually a composition of 3 different color channels. So you have one red channel, you have a green channel, and you have a blue channel. So now along with your original pixel size. So let us say if I have 100 into 100 pixels here, in grayscale, that will just be 100 into 100. If it is a color image, that will be 100 into 100 into 3. One red value, one green value, and one blue value. I'm just going to open up my paint here for a minute. Please let me know if it is visible. Is my paint screen visible? Anybody? I've opened up a paint window.
Yes, ma'am. It's visible.
Okay. So now supposing, I just put in some kind of a color here. Let me choose a grayscale. We look at the properties of this. Okay. So for this shade of gray that I've opened up, it is all 195, 195, 195. If I'm going to go with a white pixel, it is almost 247. If I go to complete white, the value is 255. If I go down to complete black, it is all 0. So a grayscale image will have values anywhere between 0 to 255. Instead, if I choose any kind of a colored image, maybe, I'll go with this purple color. If you look at the color coding for this purple image, it is a combination of 163 in the red channel, 73 in the green channel, and 164 in the blue channel. Okay. So RGB images have 3 different channels. Grayscale images have a single channel. Going back to our slides. What this basically means is, if your input is going to be color images, the pixel size, your channel size, so basically the number of nodes you're going to have at your input layer is going to be even more. And if you look at, a typical iPhone picture, even the very basic quality of an iPhone, we are not even talking about the really high quality or latest models of iPhones. Even a bare minimum iPhone photograph has a resolution of 3024 into 2448 pixels. Here, we are talking about simple images, 64 pixels by 64 pixels. That itself led to 4096 nodes, which in turn needed over 2 lakh weights. Now think of one small picture that is taken by a phone, which has some really good resolution. This is the number of pixels. This multiplied by 3. If it is a color image, that is just the number of nodes at your input layer. Okay. So the kind of real world data that we are working with is massive. And that is the reason why, your deep learning neural networks actually take a lot of time in order to train and in order to give out some kind of a result. Also, these recent advancements in deep learning is because right now we have extremely good processing capacities and very good storage capacities as well. Even, normal people like us, we are probably going for i7 kind of processors. We have around 1 terabyte of hard drive space on our systems. So if you want to train a deep neural net, you will obviously need to have very good chip capacity or processing capacity. You are going to need GPUs. I'll show you a little later why the whole neural network architecture involves a lot of matrix operations, lot of math is involved. So for you to be able to do all those matrix operations quickly and be able to train your network, you're going to need GPUs, you're going to need really high processing capacity, very good chipsets. Also, you're going to need very good RAMs and storage. And like we all are noticing, maybe, over the last 10 years, there have been huge technological advancements. So this is also leading to the rise in the kind of applications we are seeing from deep neural nets. Okay, so now, the base that we have set so far is regular neural networks. You have your input layer, you have multiple hidden layers. There are many lakhs or sometimes, millions or billions of weights that are involved. You need to initialize all this, and then they are going to be modified with every round of training. So the problems with your regular neural networks, if you increase either the number of layers, you're going to obviously end up with too many weights. Learning becomes very, very difficult. It takes a lot of time, also requires a lot of resources. Instead of your simple grayscale, if we move on to color images, the problem becomes, 3 times more. You have 3 different channels. So what was, some 2 lakh weights in the previous slide is now becoming 61 lakh weights the minute you make it a 3-channel RGB image. Also, if your data set size is huge, instead of having 1000 images, let us say I have a 1 million images in my data set. Each single image has to be passed through the network with all those weights. So, even just one round of training might sometimes take many days of time as well. So these are some issues with our regular deep neural networks. And, one reason why they're not really suitable for image data. So regular deep neural networks work extremely well when your data is in the form of tables. If your data is more unstructured and richer, like image data, or maybe moving data, let us say you have a self-driving car, it is getting a lot of input in real time from multiple directions. So if this kind of data, or like your voice activated systems, let us take Siri or Alexa, if it is speech data, everybody speaks with a different accent, they speak at different speeds, different languages. So all this data is really rich, unstructured data. And for this kind of data, normal neural networks are probably insufficient. And that was why the whole concept of CNNs came up. Now, before I tell you how a CNN works, I want to spend a little time on trying to make you understand, what are some challenges we might face with image data. Let's, maybe imagine, let us say, a 5-year-old child who has never seen a swan before, and I show them this picture, and we are trying to teach them this is how a swan looks like. Okay, it has this oval structure here, it has this nice long neck. This is how probably its face and beak looks like. Okay, again, actually, this is in fact how we as human beings learn. Maybe we don't codify it, we don't put it in the form of rules, but right from the time that we are babies and we are exposed to a lot of stimulus from the outside environment, there's a lot of knowledge representation, retrieval and extraction that keeps happening within our brain neurons. We are trying to understand how our brains work and then trying to teach a system to work in a similar fashion. So let us say I use this image as my base image and try to teach somebody who has never seen a swan before that this is how a typical swan looks like. And let us assume they have learnt well. Now, supposing we show them this next picture of a swan, pretty much, maybe they might be able to make out because the neck still looks like, similar fashion. The beak is also kind of similar. Maybe that oval structure is still retained. So somebody who learned using the previous picture might still be able to make a decent guess that this is also a swan. But now let us look at, some maybe a slightly more different images, which are still of a swan, but then whatever information that we told you or the way we trained you is now no longer insufficient to recognize that this is a swan. Although this is a swan, it is no longer having that exact same structure that we showed in the previous picture. The beak is kind of bent backward. The oval structure, around the body, it is also not clearly visible. This is another picture of a swan here on the right-hand side, where the eyes are really visible. The beak structure is kind of popping out. So if this was the image that I used for training my network, then if I supply this image, it is going to be very difficult for that network to understand that this image and that image are of the same animal. Okay. Now, supposing this is one more picture wherein we have brought in a color difference. We were teaching them that, this is how swans look like, all nice and white and fluffy. Now here we come to a black swan. That itself will throw the network away and it will misclassify this as something other than a swan. Now, these are even more complex images of pretty much the same concept. This is still a swan, but, in a very different pose and position. This again is a swan where you don't even get to see its neck. It's kind of hidden within the body. This maybe, somebody who has seen the first picture will think these two images are also swans, the two images towards the bottom. They are fitting the exact description we gave. It has a long neck. It has this oval structure. This one actually has the long neck. It has the beak and it has the oval structure. But then in reality, we know that this is just a float and this is actually a tent. Okay. So what we are trying to say is with image data, a lot more challenges come in. Okay. even when we look at our own pictures, let us say, we are trying to do facial recognition. The way we look kind of changes on a daily basis, depending on how we are dressed, maybe, presence of makeup or no makeup, the kind of light that is there in the background, what is the background image, are there other people within the picture, what is the mood of the person. A picture of a person smiling is going to be very different from the picture of that same person who is frowning or who is crying or who is sad. So although they are all the same pictures of the same person, every picture, the values within the picture are going to be very drastically different from one another. So there are these extra set of challenges that come in when we are trying to deal with image kind of data. Now, this is one more picture, where I'm trying to probably drive home the point that image data can get extremely confusing. This actually is data that is being used to train a neural network to identify this specific form of a dog called a chihuahua. But then if you notice this first image and this third image, these are actually cupcakes. But then you look at this picture with the eyes and the nose, this looks very close to this image of a cookie. So, if this is going to be your input data set, and later on, if you supply this kind of a good day cookie to your system, it might classify it as this particular dog also. Okay. So our regular way of training a neural network is now insufficient. So what do? What we want to train the system now is to make it learn by itself. Instead of me telling that a swan has this kind of a neck, this kind of a beak, and this kind of a body, I will just dump maybe 1,000 images of swans at the network. We want the network to learn by itself. Okay. And for being able to do that, that network should be capable of somehow representing that information or the features that are embedded within those images. Okay. So like we said, regular networks are insufficient. One, the number of weights becomes extremely huge. A picture of a cat at the left corner is very different from a picture of a cat where the cat is in the right border. With a regular neural network, it won't be able to make that distinction. For us, wherever that cat is, it is still the image of the cat itself. So regular neural networks can't handle images where there is some kind of translation involved within the image. Also, one very important point is a lot of spatial information is lost. We saw a few slides back that, whatever your image is, ultimately it is going to be stored in this kind of a matrix form, a 2x2 matrix. When we do that, a lot of information about what is beside, what element within the picture. Now, if you notice this picture towards the bottom, maybe, beside one petal, the closest element happens to be another petal. Maybe beside these clouds, the closest element happens to be some other white kind of a clouds. When I convert this image into pixel values, and if I try to flatten it in the form of a 2x2 matrix or vector form, this information, spatial information as to which feature is existing beside which feature. These leaves are probably beside these petals. That kind of information will be lost. So we don't want to transform these into strict 2x2 matrices anymore. Also, we want to somehow make use of this spatial information in order to recognize that, okay, this set of pixels is probably a flower. This set of pixels is probably a cloud. So we want to make use of that spatial information as well. So now let's go into the actual convolution operation. And this here a small background as to how the whole convolutional neural network or the ideology behind it started. So there was some experimentation done on cats. They put in some electrodes into a cat's brain, and then they exposed it to some form of light stimuli. They had a screen here, and then they were flashing these lines at various angles, on, off kind of a thing, and then trying to understand which parts of this cat's brain were lighting up, or how was it actually trying to recognize that, maybe a light is on, is the light moving from top to bottom, or is it able to even recognize that a light is on or not. So in terms of this research, what they understood was certain cells within the cat's brain were able to recognize simple stimuli at certain angles or locations. And then when it came to movement, maybe, if that small line of light was moving from top to bottom, certain other parts of the brain were actually being activated, and these cells were dependent on those simple cells. So the first set of cells that are being fired were called as simple cells, and then the cells that are involved in detecting movement were based on the activation they received from these simple cells, and they were called as complex cells. And in fact, for this work, Hubel and Wiesel even won the Nobel Prize. So now this kind of a concept that certain parts of your brain are involved in identifying the more simple features, and then a combination of these simple features at a more later on level actually helps you in identifying more complex features, is the main idea or the gist behind the convolution operation, which is used within a CNN. So what we want to do is we want to use the properties of the images. We want to make sure that pixel information and their neighborhood information is not lost. And then we try to analyze this information by making use of something called as a filter. So now, from now on till probably the end of the session, we are going to use these filters extensively. Okay. So what we are trying to do is we are trying to take an image and then trying to use a lot of filters on top of that image. And these filters are what will help our neural network in learning at an initial stage simple features, and at a more complex stage more complex features. For example, just imagine maybe a face. Okay, if you break it down into really, really small features, okay, maybe we have one small slant towards, at the corner of our nose maybe. And then supposing, maybe the eyebrow, this could be a horizontal line. Probably this jawline could be one slanting line. So when we break it down to really, really small features, my neural network at the initial stage might be involved in picking up all these really small features. And then at a later stage, we can combine some of these features together in order to identify a more complex set of features. So probably, one horizontal line and then one curved line and one more curve put together, that becomes an eye. Okay? And then one set of slants, probably this actually indicates a nose. So your earlier layers within your neural network are actually involved in learning really small, simple representations. The later on layers of your network will combine these simple representations together in order to understand more complex parts of the picture. So let's try and understand how that happens.
Ma'am, PPT sharing is...
Yeah, I stopped. I'm going to come back. Okay. It's visible, right, Amita?
Yes, ma'am. Yes, ma'am.
Yeah. Okay. So now what a convolutional neural network is going to do is it is going to use something called as a filter. Now, before, I show you the filtering operation, let's even talk about, let us say the regular filters that we see around the house. Maybe we have a filter within our AC. Its job is to probably stop, a lot of dust from getting in or to capture the dust. We have filters within our water filters, or, in the regular cooking, we use a lot of filters. Depending on that filter, some kind of information goes down and certain information is retained at the top of the filter. So in a similar sense, when I apply these numerical filters on top of my image data, it is going to pick up something specific based on what that filter is. Okay, so we're going to see, how a filter works now. The basic architecture of a convolutional neural network, these are probably the most common layers that you're going to notice. You will have your input image data at the input layer. This will be followed by one or multiple convolution layers. Each of the convolution layers will make use of these filters or kernels in order to identify small features from your data. Somewhere in between, we might use a lot of pooling layers. Towards the end of my CNN architecture, we are going to have some fully connected layers. So we're going to go through each of these layers in detail. Now, for the rest of the discussion, we are sticking to a really small image, 28 by 28 pixels. So those of you who have calculators, you can maybe, calculate number of input layer nodes. That is going to be 28 into 28 into 1. We are calling it grayscale. So it doesn't have 3 RGB channels, it has only 1. So 28 into 28 into 1 will be the number of input nodes. And data for a CNN network is typically supplied in, we refer to it as a tensor instead of a vector or a matrix. Like we said, if instead of grayscale, this was a color image, this would have become into 3. Okay, so now the power of a convolution neural networks comes from this convolution operation. Simple words, what it means is we are making use of some filters on our original input image. Each filter is, helping us in identifying some important feature within that particular image. Again, if we go back to our SWAN discussion, now I'm not telling my system or my network that a swan has a long neck and it has this orange beak and it has an oval body. We are not giving it that information. We are just feeding it the images of the swans. The network itself is learning that any picture of a swan will have all these kind of image, features most of the time. This orange kind of a beak or this long neck. So that identification or recognizing of those features is being done automatically by making use of these filters or kernels. So now filters are, at the end of the day, nothing but simple matrices, 2x2 matrices. It can be a 3x3 matrix. It could be size 5x5 with some random numbers initialized. Okay, most of the time, these numbers range in between, 0 or 1. You will actually notice certain filters where, the numbers could be even like -3, -5. And once again, one important point to keep in mind is maybe, for this discussion, we will look at some common filters. But in reality, within a convolutional neural network, the exact kind of numbers that are being used in each of the filters is something that is not known to us. Okay, so this whole deep learning or maybe neural networks, people still refer to it as some kind of a black box learning. That is, you give the input, you train it till you get the correct kind of output. But exactly how is it learning? What is happening within the various layers of the network? This is something that we are not really aware of. What are the initial weights? What is happening to those filters after multiple rounds of training? How are they getting modified? What is the value of each filter? Which filter is helping in identifying which feature? This is information that is not strictly known to us. We give an input, we get the expected output. It is almost like, how we as human beings function. We probably, maybe supposing, you take a child, you teach them 2 table, you make them repeat it. After a week, they're able to give you the table of 2. But exactly within their brain, how are the neurons firing? Where is this information stored? How are they picking it up and then reciting it back again? Is something that, a lot of work is still going on in terms of what actually happens within our neurons and synapses. In a similar sense, we know what are the initial values of the weights and the filters we started with. We know our input images. We know what output we expect. Exactly how all these filters are being applied and which filter is working on which part of the image is something that we might not really understand. Okay, so that is the reason why they're termed as those black box kind of learning. Now the main most important operation within your CNNs happens to be the convolution operation. It is nothing but taking your image pixel values and doing matrix multiplication with whatever filter size that you have chosen. So if you have a 3x3 filter, you have your original image and then you have this 3x3 matrix, you are going to repeatedly multiply all your pixel values with this 3x3 filter. The output that comes out of this matrix multiplication is what helps the network in identifying any one feature within your network. So I have one example here. Let us say, this is my image. Typically, it would be 0 to 255. We have chosen simple numbers here. And again, we have initialized one random filter. So this 3x3 that is kind of given in dark blue, matrix multiplication with this particular, actually element-wise multiplication, I'm sorry. So we are going to multiply element-wise with this filter or kernel. And this is the output. This is what helps us in identifying the small, minute features within the image. So if we just work it out, this is going to be 2 into 1 plus this 4 into 2 plus 9 into 3 plus 2 into minus 4 plus 1 into 7 plus 4 into 4 plus 1 into 2 plus 1 into minus 5 plus 2 into 1. This finally works out to 51. Next, instead of this dark blue square, we are going to move it by 1 pixel. So now the second time I apply the filter, it will be on top of 491,144,129. And we do this kind of a similar multiplication once again. That will give me the output for this particular cell. If I consider this part, the bottommost 3 by 3, 292,513,485 and multiply, I'm going to get the output of this particular cell. Okay. So here we are showing it for one more calculation for the next set of pixels, and the answer becomes 66. We can actually spend some time maybe on doing it for this 91 for this entire set. So once this line is over, the filter now moves on to this batch 214,112,735, and then the filter will be applied on this part 144. So what you're doing is you are slowly moving from the left corner to the right corner, top to bottom, over the entire image. You are scanning, or maybe you're applying this filter in order to pick out one small relevant piece of representation or feature from that particular image. So this is the first level of features that will be learned when you apply any kind of a filter on your image. Now moving on, this is a small animation that actually is helping us visualize that operation. So if this was my original input image and this is my filter, the filter was first to be applied on this part, then slowly move on to this part, then move on to this part, then slide down, and then be applied on the rest of the image as well. The same calculation is being shown once again. So it pretty much covers the entire image size. This is a 3D representation of the exact same concept. You have this matrix, maybe your 3 by 3, because we are using this 3 by 3 filter. So this 301 into this minus 101, then it slides to this part, then it slides to this part, and then keeps sliding so forth till it comes to this end. And then it is going to move 1 pixel down and then comes here, and then move the next pixel down. So, you can probably imagine that if your input image size is huge, okay, there will be many of these calculations involved. So just for this one cell, you have to do these many multiplications in order to fill up each cell. Obviously, a typical neural network will have to do maybe some millions of these kind of multiplications and calculations to process one single image. Now, if your data set has, let us say, 1,000 images, all those million calculations, it will have to do 1,000 times once again in order to finish one round of training of the neural network. Then back propagation happens, the weights are modified. Once again, all those million into 1,000 calculations from the front to the back. So it's very computationally intensive. Now, in the convolution operation itself, certain important parameters to keep in mind. What kind of filters are we choosing? Sometimes people also go in with some kind of extra padding. What kind of stride are you choosing? And what is the activation function that you're going to make use of? So these are important concepts that go along with the convolution operation. Now, filter sizes, typically, we can have like a 3 by 3 filter. People also use 5 by 5 filters. In fact, I'll show you one very famous and common CNN architecture, the AlexNet. Over there, some filters are sizes 11 by 11. People typically use these odd sized filters. Now, this is one example of a very famous filter, 111000 -1 -1 -1. What this particular filter helps you. So when you put this filter on top of an image, it helps you in identifying what are all the vertical lines or the vertical edges within your image. This is one more filter that helps you identify the horizontal lines within your image. Sobel and Shar filters also are very popular. Again, these are some of the well-known filters. In reality, most of the filters within your CNN might be completely hidden within that black box. We might not know what are the values inside each of those filters also. So now, for example, if this is your original image, they have done the convolution operation with this particular filter. So this image, you will have to once again imagine it in the form of pixels. And because this is color, 3-channel RGB image, each of those values multiplied with these kernel values, the output that you get is this particular image. And if you notice, most of the information is gone, but this particular image is able to detect where there are some kind of edges within your image. There is an edge here, there is an edge here, there is an edge here. So only the edge information is being picked out when I apply this particular filter. Now let us look at one more filter. The same image, the same convolution operation, I changed the filter. This time, the output that we get is a much more sharper image. Okay, so basically like this, like edge detection, sharpen, vertical, horizontal. Let us say you use 1,000 different filters, you are going to end up with 1,000 different features that have been learned from that image. I'm going to, maybe take you to one of these online visualizations that are available here. Is this screen visible, everybody?
Yes, ma'am.
Yeah. Okay. So whatever the picture that actual picture is this, the small square that you see towards the right, really small, maybe I think this is a 28 pixel or maybe even lesser image that you see onto the right hand side. It has been blown up for the purpose of this visualization or animation. These are all the pixel values. So this leftmost, and if you notice, wherever I'm moving my cursor, the same pixel is being highlighted on the right hand side image as well. So we have this pixel maybe with some 128 value. This pixel has a value of 131. So this is my original image. This is the pixel form of it. This is the actual values that are stored in the pixels. On top of this image, they are trying to use this particular filter, 0, -1, 0. So, take every 3 by 3 here. I know the numbers are extremely small, something like 250, 250, 247, 244, 161, 137. So you take this 3 by 3 and then do the convolution operation. Like that, you keep moving over the entire image, left to right, and then you come down to the second line, once again left to right, come down to the third line. Okay, so you keep doing those set of multiplications, and what you get after doing this particular convolution with this sharpen filter is this output image, where a lot of with a lot of intensity you are able to see, or this particular input image has been sharpened. Now instead of this sharpen filter, let us use maybe let us use a right Sobel filter. Again the same image, but the filter values have changed. You see the output. This is helping you pick out the features that are there towards the that have a predominantly right tilt as such. If we use another filter here, just one more, I'm going to use the outline filter here. Okay, now this is helping me identify what are all the outlines as such. So the point here is we are not trying to learn where an eye is or where a nose is or this is the hairline. That is not what we are trying to learn. We are trying to learn minute aspects of the image. There is one small slant here, there is one small straight line here, there is one slant here. So at this level we are trying to learn information from the image at the initial layers. This information can be put together, so you can combine this information towards the more later on layers. That will help you in identifying more bigger complex features as such. Okay, so moving back to our slides. So that was a visualization of how filter or kernel on top of the image, the convolution operation, what kind of output you get. Along with the filter itself, 2 or 3 more important concepts that are applied along with the convolution operation itself is sometimes people make use of padding. Okay. If you see this image here, there is this whole border that has been added and they just append it with zeros. So what padding means is you're trying to increase your original input size. The reason for doing this is, if you notice here, this was my original input image 1, 2, 3, 4, 5. This was a 5 by 5. I did convolution operation with a 3x3. My output was of size 3x3. So if we do 2 or 3 rounds of convolution, my output image, my output size might become extremely small. So at certain points of time, they might want to retain the size of the image. In that case, we make use of padding. So this is nothing but, a set of extra zeros that are added on all sides of the image. This is to make, especially when your input data is very small. Just after 1 or 2 rounds of convolution, you might be left with extremely small information, which might not be sufficient for the classification purpose. So where your input data set size is small, the size of the image, okay, there we might need to go in for this extra padding. One more important parameter when you're training or when you're applying the convolution operation is, do you want to do it with a stride of 1 or do you want to do it at a higher stride level? So stride basically, let us say if it's a really tall person, he can probably cover a lot more ground than maybe a short person can. So a stride of 1 means it is just gliding over 1 pixel by 1 pixel, what we have used so far. If I'm saying a stride of 2, it will work on the first 2 by 2, then skip 2 pixels and then work on the next set of 2 by 2s. So you can set up different stride values. If you have very huge data, if your input image size is very big, it will take, really long time for your network to train. In those cases, using high stride values might help you in doing quicker training. So that is the reason for using those stride values. Now, one very, very important concept that goes along with CNNs is the kind of activation function that is used. Like we said, maybe we have billions of neurons in our brain, but the minute, I look at a picture or maybe I get in some smell, only certain part of our brain or only some of those neurons are activated. In the similar sense, you might have a lot of nodes at your first layer. You only want certain nodes to be activated in order to identify certain features. So for that purpose, the most common activation function that is used is the rectified linear unit, RELU. Some people call it RELU, some people refer to it as RELU. So the rectified linear unit activation function, you are going to, once you apply it on top of your filter output, what it does is, any number that is greater than or equal to 0, it will retain as it is. Any filter value, the final output of your cell that you get, that is less than 0, will be converted to a 0. So if you see, if this was my output after a convolution operation, 0, 1, minus 4, 0, 2, 0, minus 1, 4, 3, after the ReLU activation function being imposed on top of this, the 0 stays 0, 1 because it's a positive number stays as 1, minus 4 which is a negative number becomes a 0. So 0 to 0 will stay the same. This minus 1 once again becomes a 0. So this filter output passed through this activation function gives you a new filter output, and the main purpose of using this is in order to maintain non-linearity. Okay. Now I have one image here. This was the output that we got after a single convolution operation with a filter. Wherever you see, slightly darker pixels are those values where there is a negative number. Where you see slightly brighter ones are the white or positive values. Using ReLU activation function on top of this will give you this particular output. So only the non-negative values will be retained. All the negative values are going to be converted into zeros. So what we have covered so far is first the convolution operation. You take one small filter, you apply it over your image, and you get a smaller feature output. That was operation 1. When you do that, you can choose different kinds of filter sizes. Sometimes you might choose to also have some extra padding around the border of the image. You can either go with a regular stride of 1, or sometimes you might choose to go with higher strides. That was what we have completed so far. One more common layer that you are going to notice within a CNN is a pooling layer. Okay. So again, this is a layer that performs sampling in order to reduce the input dimensions. Like we have been saying, each of these layers is going to involve thousands or sometimes even millions of nodes. So as we move through the network, we want to try and reduce the size of the data that is passing through various layers. For that purpose, we use something called as a pooling operation. And Simple, logic behind doing this is we want to decrease the number of parameters. If I have to train, 2 lakh weights at each layer, it might take me a month also. But if I have 2 lakh weights at the initial layer, if I'm able to bring it down to 10,000 weights towards the final layer, that will help me in quickening my training process as such. So it reduces the learning time, the amount of computation that is required. It also reduces the chance of overfitting happening. And there are 2 or 3 different kinds of poolings that are possible. We can either do max pooling or min pooling. Sometimes we go with average pooling. So let's see an example. If I'm doing a 2 by 2 max pooling, what it means is whatever output I have, I'm going to break it up into these 2 by 2 sizes, and whatever is the maximum value in each 2 by 2, that becomes the output. So this entire 4 by 4 is now converted into this 2 by 2. So from the first 2 by 2, the highest number is 100. From this, it is 184. In this, all the values are same, it stays at 12. In this right subset, it is a 45. So if I go with max pooling, this 4 by 4 size now is reduced to 2 by 2. So I've cut down the size of or the number of neurons needed by half, basically. Sometimes people also go with average pooling. Whatever are these 4 values, you can just take the average of all those values. Again, average pooling, max pooling, this is one more round of computation that becomes necessary. Towards the end of your CNN network, we usually notice a fully connected layer, which is usually the typical last layer within a CNN network. And this is where the actual job happens, image classification. So one simple CNN architecture, this is how it would look like. You have your input image, you pass it through a convolutional layer, that is, you are doing all those filter multiplications here, and then applying the ReLU activation function on top of it. This will learn some low-level features. You're passing it through a pooling layer in order to decrease the size. This decreased data, once again, we are passing in through another convolution layer followed by ReLU activation. So this will learn slightly more complex features. Once again, this passes through some kind of a pooling layer. This becomes input for a fully connected layer. Over here, it works like a normal neural network. This final output layer is what gives you your final classification. Now, like we said, the whole convolutional neural networks, they started becoming, this whole space blew up probably in 2012. There's this typical competition, very famous competition in the computer vision area that is conducted called as ImageNet. And the 2012 competition was won by the people who proposed this AlexNet architecture. So this was the first time convolutional neural nets started becoming extremely famous. And also people started realizing that instead of normal neural networks, using convolutional nets will give immense benefits in terms of working with image data. So if you look at this architecture, you'll actually understand the amount of computing that becomes necessary with these convolutional nets. Your original input image size, okay, one single image, this could be 1,000 images, one after another. So this is 227 by 227 pixels. It's a color image, so 3 channels. On top of this, 11 by 11, okay, size of the filter is 11 by 11. 96 different filters of 11 by 11 with a stride of 4 is the convolution layer that we are applying on top of this input layer. Then we are going with a max pooling layer. Once again, we are applying convolution with 5 by 5 filters. So, if you notice the filter sizes, first layer of convolution, we are using 11 by 11 filter, 96 filters in total. The next layer, we have 5 by 5 filters, 256 filters in total. The next layer, 3 by 3 filters, we have 384 filters in total. So there are 5 convolutional layers, each convolutional layer followed by a max pooling layer. And towards the end of the network, we have fully connected layers with 4,096 nodes each. Okay, there are some 1.3 billion parameters or something that the network has to learn through this entire training process. This is another visualization of the same AlexNet architecture. This is my original input size, 11 by 11 filters, 96 in number. So this 227 by 227 by 3 actually now becomes, the input size now becomes 55 into 55 into 96. Once you do 3 by 3 max pooling, this size is reduced to 27 by 27. On top of this, you use 96 filters of size 5x5. It becomes 27, 27 to 56. Once again, we go for pooling. Once again, we go for convolution, pooling, convolution. Okay. So the people who proposed this AlexNet architecture, they made use of these 5 convolutional layers with these sizes of filters, followed by max pooling, followed by 2 fully connected layers in order to do the final classification. The final classification is a softmax layer with 1000 nodes. That means whatever images are being supplied or are being processed through this particular network, it will be able to identify or classify 1000 different categories within those images. So now let's move on to understanding, where CNNs are being used. Okay, pretty much all around us, we are seeing a lot of CNN applications. Most important in image recognition. The minute you switch on your phone and if you're trying to use your face detection, that is nothing but image recognition. Is it the same face that has been fed into the system? The next is object detection. This particular picture has image of a cat and a dog and maybe a chair. So detecting various different kinds of objects within a given image. Trying to do visual search. A lot of us actually, in fact, do this Google reverse image search. Even, apps like Myntra these days, you can input one picture of whatever dress you like. It will suggest similar kind of dresses that are available on their platform. So visual search, recommender engines. Again, pretty much all of your shopping apps. If I go and, place an order for one specific kind of a product, based on that image, what are other similar models that I might be interested in? Those kind of recommendations that come. Almost all of your facial or object detection that happens on social media, whenever you upload an image onto your Facebook or onto Instagram, the ability to tag, those faces, even, our phones, in fact, from our gallery, they are able to pick out all these 100 pictures have, this particular person also present in these pictures. So those kind of facial recognition tasks. And then surveillance especially. In fact, this was probably out in the news a few months back. China probably has really state-of-the-art surveillance systems at a very low level. Almost every street corner, every single traffic light is... we do have cameras right now, but their cameras are also built in with all these kind of surveillance techniques where in real time, anybody who's passing through on the street, they will be able to zoom in and identify who that person is. That is, they're able to recognize maybe, every single face from 1 billion faces and be able to pinpoint who that person is. So very high grade surveillance already being done through these kind of face recognition systems, which are built on top of convolutional neural networks. A lot of applications in the medical area as well. If you supply, maybe some thousands of X-rays or MRI scans, learning or trying to detect what normal X-rays look like versus what X-rays or scans of diseased people might look like, trying to assess the risk, how much of health risk is present through this image data. Not necessarily image data, CNNs can also work with your regular structured data as well. So these are some of the applications that we are already seeing out there in real life. Most of us do know about, Tesla's self-driving cars. So this Tesla car, every car comes with around 8 cameras that are attached on different portions of the vehicle itself. So all of these 8 cameras are taking in a lot of visual input in real time, and then that is being analyzed, and the CNNs built within those, the autonomous driving systems, they are able to detect, okay, there is a person in front of the car, or there is a traffic junction at this particular place. Maybe, there is a huge vehicle in front, and because of that, maybe, the car has to apply a brake. So this real-time object detection, how close they are, what is the actual object that is there. All of this is being possible because of the rapid advances that have happened within the CNN area. So convolutional neural networks are finding a multitude of applications across domains. And in fact, most of us are interacting with some kind of a pre-built or pre-trained, a very minor scale of a CNN that is already present in most of our smart devices as well. So, this is again one more application of CNNs for face recognition. Dr. Amita, how much time do I have to finish, this session, and maybe, just
ma'am, you can take for 10-15 more minutes.
Okay, so I'll just I'll not run this entire CNN because it takes minimum of 20 to 25 minutes, and we can actually try out certain practical simple lab examples as such on Google Colab, which is free. So all you need is your Gmail account. So this is a simple CNN that we are trying to construct on this Canadian Institute of Research set, CIFAR set. Again, the most common packages that are involved happen to be NumPy. And then especially for deep learning, wherever neural networks are involved, we need the TensorFlow framework and the Keras framework as well. From Keras, we are importing the sequential model. So sequential model is kind of what we saw in one of these pictures, a series or sequence of different kinds of layers put together. Input layer followed by convolution layer followed by pooling layer. Okay. It's up to you how complex or how big you want your network to be. So now let us just look at the kind of layers that we are actually including within the small deep CNN network that we are trying to build here. We have a convolution, 2D convolutional layer. We have a flattened layer, we have a dropout layer, and we have a dense layer. In terms of pooling, we are using one max pooling layer, and we are using global max pooling layer as well. And then, there are a lot more hyperparameters to keep track of. We didn't even touch upon that concept. Batch normalization, various Adam optimizers and regularizers. So we're not going to go there. Very complex. And then obviously we're going to need a whole lot more time. So once I've connected to Google Colab and then run it, at least the first 2-3 cells, typically finish off really quickly. But then the actual cell where I'm trying to do the real training of my neural network, that is going to take a lot of time. So let me show you the CIFAR dataset. So it has all these lots and lots of images available. So there is one big batch of images of airplanes, a big set of images on automobiles, another set of images of birds, a set of images that have dogs in them. So this data set is what is being passed into our deep learning neural network, so that it will try to go through all these images which have already existing labels. This is image of a car. This is image of a dog. So it is trying to learn that, okay, a dog image will have these kind of features within that particular image. So that is the training that is actually happening. So we have downloaded or imported actually the data set. Some form of normalizing that happens. The pixel values are divided by 255. This makes it easy for us in order to do our matrix multiplications at the next stage. This is where we are actually building our model. So if you see, first I started off with a empty sequential neural net. The first layer that I'm adding is a 2D model. I'm using a 4x4 filter, and I'm using 32 such filters here. So 4x4, 4x4, 32 different filters, each filter trying to learn a different kind of a feature. We have no idea what each of those 4x4s look like. We only know there are 32 4x4 filters. And after doing the convolution operation, we are passing it through this ReLU activation function. The output that comes from this first convolutional net layer is being passed through a max pooling layer with a size 2x2. So every 2x2, that is, every 4 pixels, you're going to do max pooling and reduce the size of your data. This reduced data is now once again being passed into the next convolutional layer. Again, at this layer, I have filters of size 4x4, and I have 32 different filters, and we are using the ReLU function. This output is once again being passed through a max pooling layer. That is being passed through a flattened layer. So instead of having this 2x2 structure, now we are converting it into a one-dimensional vector format. That is being passed through a single dense layer. Dense is a fully connected layer. So whatever is the number of nodes at this flattened layer, all of them are once again connected to 128 neurons at the next layer, and through the use of the ReLU function. Then the final output, okay, where the final prediction actually happens is once again a dense layer. That is a fully connected layer. It has these 10 neurons, and here we are using the soft max activation. So like we said, The convolution layers mostly make use of the rectified linear unit ReLU activation function. Whenever we are trying to do some kind of a classification, we typically make use of the softmax activation. So most final output layers in a lot of networks that you notice will use softmax. What softmax does is, supposing, I given an image, it will give me output as, this could be image of a cat with 0.8% probability. This could be image of a car also, maybe with 0.01% probability. This could be image of a human being with 0.05% probability. So the softmaxes, it is going to give you the classification along with the probability that that particular image could belong to one of your output labels. Now, whichever is the highest probability, obviously we will say that this image belongs to that particular class. So now, if I'm trying to do my training, okay, here if you see this epochs 20, that means this entire process, take an image, pass it through the entire neural network, learn, get the error, do back propagation, change the filters, or not reinitialize, slightly modify the filters and the weights. Once again, from forward to backward. So this entire process is going to run 20 different times on all the input images. And if you just notice the number of parameters or weights it has to learn. At the first layer, it has to initialize 1568. That is this 32 into 4 into 4. That is what, the total 32 4x4 filters that you're trying to learn become 1568 parameters. At the pooling layer, it doesn't have to learn anything. At the next convolution layer, once again, okay, it will have to learn around 16,000 parameters. The next max pooling and flatten layers, no learning involved. At the first fully connected dense layer, it has to learn over 1 lakh weights. The next dense layer, 1290. So if you notice, these are the total number of variables, maybe in simple programming language, 1,21,802 numbers. It has to first initialize. By the time it finishes the training, it will come up with the most optimum values of all of these parameters. And if you see, first one round of training is already over. It is running here. And it took around 63 seconds. That is roughly over a minute. So now if I've asked for 20 rounds of training, this one step is going to take close to 22 to 23 minutes. And it will have learned how to classify each image. So this is a simple demonstration of how a CNN network works. I'm just going to really run through this autoencoders, since that was also mentioned as one of the topics being covered today. So autoencoders is one more flavor of these deep neural networks itself. Okay, there are like two really differentiating properties in comparison to your regular neural network. The number of nodes you have at your input is the same as the number of nodes at the output. That's the first point, that is very different from autoencoder with other networks. Till now, if you see, maybe my input layer had 4,096 nodes, my output layer had only 10 nodes. Over here, if my input has 10, my output also has 10 nodes. Most important feature with respect to an autoencoder is you have something called as a bottleneck layer. Okay, like the neck of a bottle, which is really narrow in comparison to the remaining body of the network itself. So this is where you're trying to do some kind of constraining and trying to force that system to learn very efficient representations of the information. Most of you might have noticed, when you send an image through WhatsApp, your original image that, whatever you clicked on your cell phone, especially with the good resolution, it could be 4 to 10 MB in size, one single photograph. The minute you send it on WhatsApp towards the other side, it becomes something in kilobytes. There is an order of 100 or 1,000 magnitude compression also. So those actually use typical image compression techniques. Here, we are trying to take any kind of data. It could be image, it could be speech, it could be textual data. You're trying to find a much more compressed representation of that same input data. That is the main purpose behind the autoencoder. Some of the applications of autoencoders, they are mainly used for the purpose of data denoising, a lot of fun applications like, your filters, image in painting, information retrieval. Okay. So if this is your original input, first you pass it through an encoder. The bottleneck layer, the small layer in between, learns a very small, minute, compressed representation of your original data. Once you pass it through a decoder, it will be able to reconstruct your original input once again. Some of the functionalities, the reasons why autoencoders are used. If you make use of an under-complete autoencoder, it helps you in dimensionality reduction. Okay, so you're still trying to know all the important information that is there in the image, but in a much reduced space. So it helps you with dimensionality reduction. You also have something called as denoising autoencoders, wherein, especially if you take, your photographs, let us say of parents, grandparents, some 20, 30 years back, these black and white images that don't have much clarity or resolution. You now have some online systems where, they can clean it up and give you a much more nice clarity, a better image. So what those systems are doing is they are taking images that have a lot of noise. They're trying to learn what is the most important representation of the image after having removed the noise, and they're able to reconstruct the original image. So this is one more functionality, denoising. They also help in recognizing any kind of anomaly. So, if you just pass in multiple images and they have learned a small representation of it, the minute they encounter any kind of a different kind of an image where there is some anomaly present, because of the amount of loss in the system, they will be able to recognize or infer that there is some anomaly. So basically, disease prediction. Okay, is this an image? If I give it 100 healthy images, the minute I supply an image of maybe a tumor, it will be able to very quickly recognize that this looks very different from healthy images. So this is one more application of autoencoders. You might take damaged images and you will be able to do some kind of in-painting. Okay, so the line on the top is images where there is certain missing information, and this is after in-painting has been done by passing these input images through an autoencoder. Okay, so that's about it regarding autoencoders. And I would like to really thank, the organizers and the participants as well for this opportunity.
Thank you so much.
Thank you.
Ma'am, it was really a very nice session, like how you started from the basics and you explained everything in such a simpler way. Like whenever we try to read from books or just see YouTube videos or somewhere, it is not connected that much, like, and it is very difficult to get all the things properly at one place. So it means you connected very well, like it was from very basics and it is in very simple way, and you have covered like almost all the aspects of the topic, which is very application kind of thing. Whenever, at least as a math student, when I used to read something, I see very small application or very less applications of that thing, but you have related it in a very nice way and showed us like how applications are there using mathematics as well. So it was a very nice session, ma'am.
I would also like to thank, Research Foundation of India for organizing and also for giving us this opportunity to be resource persons, and also big thanks to the participants.
Okay, so to all the participants who are present here, I am just sending one feedback link. Although I have sent in WhatsApp group also, I am also posting that one in chat box. So you all are requested to kindly fill that feedback form. I'm just pasting that one. Yeah. Yes, Punita ma'am, if you have any doubts or anything, or any participants want to ask any question to ma'am, you can ask or just clear your doubt. If anyone has any query or doubt which you want to ask with to ma'am, you can do that one.
Yeah. Thank you, Punita ma'am.
Okay, so if anyone has any doubt, you can please write in chat box. And meanwhile, I'm going to give vote of thanks from myself. Okay, ma'am, there is some question in chat box, ma'am, difference between voting and simulators.
Oh, I think, this is probably carrying over from yesterday's session. Difference between voting and simulators. Ma'am, frankly speaking, I was only covering the voting part of it yesterday, when we were talking about the whole ensemble techniques. Okay, so when you are taking maybe a combination of techniques, and each technique is probably going to give you a different kind of an answer, then we use the concept of voting in order to understand what is the most commonly retrieved result from all of those ensemble techniques put together, and that becomes the final output of my ensemble method. Simulators as such, to be honest, I haven't seen that concept within the scope of ensemble techniques as such. the idea I have about simulators is where we are trying to maybe simulate some kind of a situation so that, instead of having to do it in real life, through virtual means, you're still trying to get to the output or what could be the, probable output of any kind of a situation.
Any other question? Okay, so I would like to thank all speakers who have explained all the topics in a very clear and interesting manner. I really would like to thank them for spending their valuable time for this FDP. I would also like to thank all the participants who have actively participated in this faculty development program. Hope you have got insights of the various machine learning aspects. In future, we will definitely going to plan some more FDPs like this. So yeah, we can choose that. Ma'am, there is one more question, like for question or maybe one statement.
From Ms. Garima. Can we choose RNNs for prediction as well? You can, but the power of a recurrent neural network. See, basically, like we said today, we covered initially regular plain neural networks. Those are really good for prediction purpose. If you'd want to do any of these image tasks, convolution neural networks are very, very useful. Recurrent neural networks have their own strength and a different flavor to it. They are especially useful when you are dealing with data, that is kind of also has some kind of a time component over it. Let us say I'm trying to do speech processing. If I'm asking one big question, maybe to a neural network, what is the weather today? So that particular voice activation system has to process this data over various time periods as such. And sometimes, it makes use of these recurrent units within. So like we have added convolution operation today, an RNN makes use of certain recurrent units in between a regular deep learning network, especially to work with speech data and to work with NLP data, natural language processing. Because, if you want to understand a sentence, you will have to also keep a lot of background context in mind. Okay. So for those kind of situations, RNNs are more helpful, ma'am.
Ma'am, there is another question.
Yeah, I think that was probably like a continuation of, we need history and image features. What do we need?
Okay. Any other query? From yesterday's session or today's, both will be fine because ma'am only took yesterday's session. Okay, I guess ma'am now it is clear. So yeah, thank you so much ma'am for being.
Thanks once again, Dr. Amita.
Okay, so thank you everyone. So this is the end of this 5 days FDP program on essentials for machine learning. So thank you everyone for joining this session. We will meet again in some other FDP or something workshop and we will organize. So yeah, thank you so much. Session is over. Yeah. Kindly fill the feedback form. Thank you.